study the design procedure of spur gear. Friends, when we say design of spur gear, we mean to say that we have to find out the dimension of gears as shown, that is the addendum, dedendum, pitch circle diameter, clearance, tooth width, etc. etc. And all these dimensions depends on module. You can see this. Here addendum is equal to 1 times the module, that is equal to module, and dedendum is equal to 1.25 times the module. You can see this in this gear diagram, and pitch circle diameter is equal to m times tooth on the gear, etc. etc. So all these dimensions depends on module. So main key in gear design is to find out this module denoted by m. Anyhow, we can find out this module using the strength equation, and the design is almost done if module we are able to find out. So main key thing is that we have to estimate module first. Now let's see how we will do that. Suppose this is gear A and this is gear B. Now force applied by gear A on gear B is denoted by this letter P as shown, and this P is resolved into two components, PT and PR, mutually perpendicular to each other. Here PT is responsible for power transmission and PR is not, so PR is neglected. Now see this PT which is responsible for power transmission. This PT is the tangential component of the force. It induces bending stress on the tooth of the gear, okay, at B. Sorry, the tooth of it induces the bending stress on the tooth of the gear at the section as shown here, that is at the root section of the gear B as shown here. So to find module, we establish relationship between the tangential component of the force PT and the bending stress at this section, that is at the root of the tooth B, and the module is obtained then after solving this relation between the PT and the bending stress at the section of the root of the tooth B. Okay, and now let's start the process of design. Now in the first step, we will assume the material for gear and pinion. Generally, plain carbon steel is used as material of gear and pinion. Hence, by pinion, here by pinion we means the smaller of the two gear is called pinion. Okay. For example, you can choose 45C8 as material for gear having ultimate tensile strength denoted by SUT here as shown as 630 Newton per mm square taken from the data book. Similarly, you can choose 40C8 as material for pinion having ultimate tensile strength denoted by SUT as shown as 580 Newton per mm square taken from the design data book. So plain carbon steel is selected as material, and for gear and pinion we have to write down the value of ultimate tensile strength from the design data book. Now in the step number 2, we will calculate permissible value of stress for gear and pinion. Okay, so what is the highest value of stress that the gear and the pinion can withstand is called as the permissible stress for pinion and gear. We know that a single tooth of gear is said to be loaded only at the time it makes contact with another tooth of another gear. Rest of the time it is unloaded. So loading is not steady, it is fluctuating in nature. Okay. So endurance limit is considered as the stress responsible for failure, and endurance limit in case of gear is assumed as ultimate tensile strength by 3. So the permissible stress for pinion can be taken as ultimate tensile strength for the pinion material divided by 3, and the permissible value of stress for gear can be taken as ultimate tensile strength divided by 3 for gear material. Okay. Now we will now assume which member is weaker. We know that out of two members, pinion and gear, one member will be weaker and one member will be stronger. So we always need to find the weaker member. so that we can set limits of design stress for weaker member so that weaker member do not fail. So for that we have to find the Lewis form factor denoted by capital Y as shown. We have to use table given in the design data book which specify the value of Lewis form factor corresponding to number of teeth as shown here on the right side in this table. Here capital T represent number of teeth and Y represent the Lewis form factor corresponding to the number of teeth. So you have to calculate the value of Lewis form factor for pinion and gear based on the number of teeth on pinion and gear using this table provided in all design data books. In some data books, to find Lewis form factor, certain empirical relations are provided as a function of teeth. Using that also you can find the Lewis form factor. Now, based on the product of the ultimate tensile strength and the Lewis form factor for calculated separately for the gear and the pinion as shown, we have to compare these two products of ultimate tensile strength and Lewis form factor for both the member and find out which product is coming out to be lower, and that product will correspond to the weaker member, and for that we have to follow the rest of the design procedure that I am going to tell you. Now in step number 4, we will find tangential component of the force denoted by letter PT as shown. Because this load PT causes bending stress at root of tooth which leads to tooth failure at root as shown here. Friends, see these are two gears, gear A and gear B. Gear A is transmitting power to gear B, and at this instant tooth of gear A is making contact with tooth of gear B as shown. Now at the point of contact you can see tooth of gear A is applying force P as shown. This force P can be resolved into PT and PR. Here PT is the tangential component of the force responsible for power transmission only. So we need to find out value of the PT and neglect PR. So PT is given as power transmitted divided by pitch line velocity, which will be equal to P stand for here power, and divided by pi dn divided by 60, which is equal to pitch line velocity. So when you substitute the value of the d here as m times number of teeth, then you will get the expression 60p by pi mtn. So PT can be find out using this expression. If this expression as shown is applied for pinion, then here T will represent the teeth on pinion and N represent RPM, speed of pinion. And if this equation is applied for gear, then here T will represent the teeth on the gear and N will represent the RPM, speed of the gear, provided power remains same. So by applying this equation to either pinion or gear, you can find out the value of the PT. PT will come out to be same in both cases. Now in step number 5, friends, the tangential component of the force calculated from step number 4 denoted by PT is not constant. It changes during gear operation because of dynamic effect due to impact and high velocity. So we have to apply some factors to it to make correction, and the corrected tangential load is given by the term P effective as shown. Here, this P effective will be responsible for bending failure of tooth at the root section. Here, the factor CV called velocity factor accounts for the dynamic effect of impact and high velocity. The velocity factor CV can be taken from design data book using the data as shown on the right side. It can be seen that the value of velocity factor depends on pitch line velocity of the gear and pinion denoted by this symbol as shown here. You can see this. So using these formula to calculate pitch line velocity as shown, you can find out the pitch line velocity of the gear, and based on the pitch line velocity you can find out the velocity factor CV using this table. Note, friends, as an important note, point it is that most of time we do not know the pitch line velocity of gear in initial stages of gear design, so we can assume pitch line velocity of pinion and gear as 5 meter per second initially to find the velocity factor CB based on the pitch line velocity is equal to 5 meter per second using this table as shown on the right side. Friends, here CS denote the service factor which depends on type of loading and number of hour of service. It can be obtained using this table provided in all design data book based on the number of hour of service and the shock involved in loading. As shown here on the right side, using this table you can find the value of CS, that is the service factor. Now in step number 6, bending stresses at the root of the tooth are estimated using Lewis equation in step number 6. Here SB denotes maximum value of the tangential force that can be applied at the end of the tooth so that tooth do not break. In this equation, sigma represent permissible bending stress at root of tooth. This equation is applied for weaker member out of pinion and gear always. Now B here, small b is the face width assumed initially as 10 times of the module. Okay, and here sigma is equal to the permissible value of stress for weaker member taken from step number 2 as ultimate tensile strength of the weaker member divided by 3. And here y is the Lewis form factor for weaker member as already calculated by us from step number 3. So after substituting all these things in this equation, you will get beam strength as B as a function of module only. Now we will come to step number 7. In step number 7, we will equate effective tooth load as obtained in step number 5 with the beam strength obtained in previous steps. So you will get this equation as shown. And solving this equation, find the value of the module M. So when you get module, then almost problem is solved. Now in step 8, using value of the module obtained in previous step, we will find out the value of diameter of pinion and gear using this equation of module. Here dP and dg are diameter of gear and pinion respectively. TP and TG are tooth on gear and pinion respectively. And using this equation of pitch line velocity, we will find pitch line velocity in point 2 as shown. In point 3, we will find our tangential component of the force denoted by PT as shown using power and velocity taken from above as shown by this arrow. And after that, we will find velocity factor CB using the pitch line velocity taken from above point 2 using this table on right side. Then we will find out the effective tooth load given by P effective is equal to CS by CV into PT as shown by this formula. Here PT is taken from the point 3 as shown above and CV is taken from point 4 as shown above and CS is taken from step 5 discussed earlier. In step 11, we will find out beam strength SB numerically by putting the numerical value of the module obtained in the step 7. Okay, and if the beam strength obtained in the step 11 denoted by SB is coming out to be greater than the effective tooth load, then the design is safe. Otherwise, we have to go back to step 6 where we have earlier assumed the value of the face width B is equal to 10 times of the module. Okay, we have to go again back to the step number 6. Okay, here the value of B is taken as 10 times of the module, but now because the design is not coming safe, if the design is not coming safe, then we will assume the value of B as 11 times of the module this time and follow the step 7, 8, 9, 10, 11 again and again check if this condition is satisfied for safe design or not, where this condition denotes that SB, that is the beam strength, is greater than the effective tooth load. If this condition is satisfied, then the design is safe. At last, find gear dimension using the value of the module, because all the gear dimension depends upon the module, as you can see from this figure. So this was all for today's friends. Thank you for watching the video.